This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas. I want you to do something for me right now. Reach out and just touch the bottom of your laptop. Or, if you're listening on a phone, feel the back of the case after you've been watching a high-definition video for a little while. It's warm, right? Maybe even hot enough to be genuinely uncomfortable.
Yeah, and now I want you to take that feeling and scale it up, like way up. Imagine massive data centers. We're talking buildings the size of shopping malls that are entirely dedicated to housing servers.
Right. Picture the gigantic cooling towers on the roofs of those buildings. The millions of gallons of water constantly circulating through the pipes, the roaring industrial fans. All of that infrastructure, all of that heat is the physical manifestation of a massive looming energy crisis in artificial intelligence. Because what you're actually feeling when you touch that hot laptop is a war.
A literal war, yes.
We are forcing billions of electrons through tiny silicon corridors, and those electrons are fighting back. That resistance, that friction is heat.
We have essentially hit a complete thermodynamic wall. Traditional electronic computing relies on pushing matter, specifically electrons, around a board. And every single time you push matter, you generate friction. It's unavoidable.
And that is why you handed us this incredible stack of sources for today's deep dive.
Okay.
We've got historical retrospectives on optical engineering going back to the 1960s. We have an incredibly dense 2026 paper from a team of researchers in Beijing who are literally building computers out of lasers, and reports on this absolute wild west of quantum startup companies trying to run calculations on entangled cluster states.
It's a huge amount of material.
It is. But our mission today is to take all of these disparate pieces, lay them out on the table, and synthesize them to answer one really fundamental question. What if we stop fighting the friction? Like, what if, instead of using matter to compute, we use the fastest, most frictionless thing in the universe? What if we compute using light?
And the journey to answer that question is going to take us through a 60-year quest. We're going to spend a good deal of time unpacking that groundbreaking 2026 paper you brought us. The one titled A Versatile Coherent Ising Computing Platform by researchers Hai Wei, Chuan Wang, Kai Wen, and their colleagues.
That's the one with the femtosecond lasers.
Right, exactly. They use femtosecond laser pulses to solve mathematical optimization problems that classical supercomputers completely choke on. We're going to look at the staggering physical hurdles they overcame to do that. And then we'll pan out to the broader frontier of digital light-based processors and even continuous variable quantum computers.
Honestly, reading through the notes, this feels less like a technology review and more like a detective story. A story about mapping the abstract mathematical universe directly onto physical reality. So let's start at that thermodynamic wall you mentioned. We've been using silicon for decades. It feels like we are suddenly desperately trying to abandon it.
Well, we are reaching the physical limits of what silicon can do.
Right. And looking at the power consumption numbers in your notes, the core problem doesn't actually seem to be the calculation itself. It's the transit.
That is the big secret of modern computing. Moving data on and off a microchip accounts for over 80% of a modern processor's total power consumption.
Wait, 80%? Just moving the data around?
Yeah, over 80%. The computational logic, the actual adding and subtracting, is relatively cheap in terms of energy. The transit is what burns the house down. Communicating a single bit of information electronically on a chip can cost up to 600 femtojoules of energy.
600 femtojoules sounds like a rounding error. It sounds like nothing.
On its own, it is. But when you are running a large language model with trillions of parameters, doing trillions of operations a second, those microscopic femtojoules add up to a massive, literal bonfire.
So we have to look at alternatives. And you compare that cost to optical communication in the notes. When you use electro-optical modulation, basically sending that data as a pulse of light instead of pushing electrons, the energy cost drops dramatically.
It drops to between 1 and 10 femtojoules per bit.
Wow. So from 600 down to 10, that's incredible. It's like the difference between navigating a traffic jam and flying in an open sky.
That's a great analogy, actually.
Yeah, like electronic computing is a traffic jam on a one-lane highway. You've got all these cars, the electrons bumping into each other, stopping, starting, creating friction, generating exhaust. You physically cannot fit more cars on the road without widening it, and even then, they still interact and slow each other down. But optical computing is like airplanes flying at different altitudes. You can have planes flying over the exact same piece of ground, but they never interact.
Right, and in optics, that concept is called wavelength division multiplexing. You can send multiple colors of light, so different wavelengths, through the exact same optical fiber at the exact same time.
They just pass right through each other.
Exactly. A red beam and a blue beam can cross paths or travel perfectly parallel down a glass tube, completely ignoring each other. They don't collide, they don't
Yeah.
generate heat from friction.
Okay, so if the physics of light are so vastly superior for moving information, why are we only doing this now? Because I'm looking at the historical sources you provided, and people have known about these properties since the 1960s.
They have. The history of optical computing is a 60-year adventure defined by, well, incredible theoretical highs and devastating engineering lows. Back in the 1960s and 70s, researchers like Adolf Lohmann were pioneering computer-generated holograms.
For what exactly?
They were using optics to perform Fourier transforms, primarily for military image processing.
Okay, a Fourier transform is basically a mathematical way to break a complex signal down into its simpler constituent frequencies. I know that doing that on a standard computer requires a pretty heavy algorithm. Are you saying they were doing it without an algorithm?
That's the brilliant part. They realized that a physical lens naturally performs a complex mathematical operation on light just by letting the light pass through it. Because light is a wave, it naturally interferes with itself. It diffracts.
So the shape of the lens does the math?
Yes. The physical shape of the lens bends the wave, creating complex mathematical patterns instantly. There is no line-by-line code execution. The light does the math simply by existing and passing through the glass.
That seems like an unbelievable cheat code. The universe just hands you the calculation. So why didn't my first desktop computer run on lenses? I remember reading the sources about the 1980s and these shadow casting systems. I was trying to wrap my head around this. They were literally shining light through stencils.
Yeah, imagine shining a broad beam of light through a series of physical masks. These were stencils with very specific microscopic patterns cut out of them. By overlapping these projections on a sensor, they were attempting to perform parallel binary addition.
Like making shadows to add numbers?
Exactly. A spot of light hitting the sensor might represent a 1, and a dark spot might represent a 0. Conceptually, it was brilliant.
But practically impossible to scale, right? Because if you are using physical stencils to block light to do math, every time you add a step to the calculation, you block more light. Eventually, wouldn't you just end up with total darkness?
That was a massive bottleneck. The light attenuates, it fades out, the more operations you string together. Furthermore, the physical alignment was an absolute nightmare.
I can imagine.
Trying to perfectly align microscopic stencils across a whole circuit board so the light hits the exact right spot on a sensor, I mean, the tolerance for error was essentially 0.
And while the optical engineers were struggling to align their stencils and getting increasingly dim signals, the silicon engineers were just aggressively shrinking electronic transistors.
They were, and that brought on the optical computing crash of the early 2000s. The field practically went dormant.
Just died out completely.
Pretty much. The silicon industry was strictly adhering to Moore's law, shrinking electronic transistors down to nanoscopic sizes. Optical engineers just couldn't compete with that density. The wavelength of light itself became a limiting factor for how small you could make optical components. You can't squeeze a light wave into a space smaller than its own wavelength without severe issues.
And there's another fundamental issue here, too. Because to build a computer, you don't just need to move data. You need logic. You need a transistor. You need one electrical signal to switch another electrical signal on or off. How do you make one beam of light switch another beam of light on or off if they naturally just pass right through each other like those airplanes?
To achieve that, you need nonlinear optical effects. You have to pass the light through a highly specialized crystal that alters its properties under intense energy.
But there's a catch, I assume.
A big one. At the time, triggering those nonlinear effects required massive, continuous amounts of laser power. It entirely defeated the purpose of being energy efficient. Your optical computer might do the math instantly, but it would require a small power plant to run the laser.
So silicon won the war. Until AI broke the paradigm, deep neural networks started demanding billions and trillions of parameters. Moore's law began to stagger, and we are back to the melting copper wires. The industry realized that replacing copper with optical interconnects inside the data centers was an absolute survival imperative.
Right. The ambition shifted completely. Once the tech industry successfully started using light to move data between servers, which is common practice now, they started asking the next logical question.
Which is, if we have the light, why not use it?
Exactly. If we are already expending the energy to convert the electronic data into light, to shoot it across the data center, why do we convert it back to electricity to process it? Why not process the data while it is still in the form of light?
And this brings us to the core of the deep dive, the 2026 paper from the Beijing team. To understand how they built a computer out of light, we have to look at one of the hardest math problems in the world, and a physics model from 1925. Let's tackle the math first. Combinatorial optimization.
Yes, combinatorial optimization problems belong to a class of mathematics that seeks the absolute best solution out of a finite but massive set of possibilities. In computer science, many of these are classified as NP-complete.
Give us some real-world examples of that.
Think of logistical nightmares. Scheduling thousands of airline flights, routing a massive fleet of delivery trucks to minimize fuel consumption, or allocating bandwidth in a global communication network.
Let me give a very tangible example to map this out for you listening. Imagine you are planning a wedding. You have a seating chart, and you have 10 guests. Some of them are married and must sit together. Some of them are divorced and will start a screaming match if they are placed at the same table. With 10 guests, you can probably figure out the optimal seating arrangement on a napkin over a cup of coffee. But what happens when you scale that up to 100 guests?
The complexity completely explodes. It doesn't just double or quadruple, it scales exponentially.
Right. With 100 guests, the number of possible seating arrangements is a number so astronomically large that if you took the world's fastest classical supercomputer and had it check one possible seating arrangement every single millisecond since the dawn of the universe, it still wouldn't have found the perfect answer. It is mathematically intractable to calculate every single combination sequentially.
Which is where Ernst Ising enters the picture. In 1925, he proposed the Ising model to explain ferromagnetism. That's the physical mechanism of how materials become magnetic. He envisioned a physical lattice of spins.
Spins, right.
You could think of these spins as tiny, microscopic magnets. Each one can either point up, representing a +1 state, or point down, representing a -1 state.
Okay, I'm tracking with the tiny magnets. But how does that solve our wedding seating chart?
Crucially, these spins interact with their neighbors. Based on their properties, they either want to align with each other, so both pointing up, or they want to point in opposite directions. And the breakthrough realization, decades later, was that physics provides a cheat code for optimization. A physical system naturally and inevitably seeks its lowest possible energy state.
Right, like how water settles in the deepest part of a valley, or a ball rolls down a hill, it never rolls up.
Exactly. In the Ising model, if you let the system run, the entire network of spins will naturally flip and adjust themselves over and over, until the overall collective system reaches its absolute minimum energy configuration.
Let me make sure I'm bridging this correctly. Researchers realized that if you could mathematically translate your wedding seating chart or your delivery routes or your financial portfolio into this physical matrix of tiny interacting magnets, you wouldn't actually have to write an algorithm to calculate the answer. You just physically build the system, turn it on, and watch what the physics do.
That is the entire conceptual foundation of the coherent Ising machine, or CIM. Instead of crunching numbers in a traditional processor, you build a physical diorama of the problem. But they didn't build it out of physical magnets. They built it out of light.
And this is where I need you to break down the mechanics, because the leap from tiny magnets to lasers is massive. The paper talks about DOPOs, degenerate optical parametric oscillators. How exactly do you build a spin out of a laser beam?
It requires a highly specialized setup. Picture a long ring of fiber optic cable. We inject a series of individual laser pulses into this ring. Each pulse of light circulating in the loop represents one of our guests at the wedding. So one pulse equals one spin.
Okay, so I have light pulses doing laps in a glass track.
Right. And because light is an electromagnetic wave, it has a phase. When these pulses pass through a specific nonlinear crystal inside the loop, and this is the oscillator part of the DOPO, the physics of the crystal force the phase of the light pulse to settle into one of two distinct states. It's either 0 or pi. zero phase or pi phase.
And that binary choice, 0 or pi, maps perfectly to our +1 and -1 magnetic spins.
Precisely. Or rather, that is the exact mapping the system uses. You have these pulses racing around the fiber loop at the speed of light, and they are either in a phase of 0 or pi.
But the pulses are just traveling in a circle. In the wedding analogy, the guests have to interact. The divorced couple needs to know they hate each other so they don't sit together. How do these individual light pulses know about the specific constraints of the problem?
That happens through an external control loop. As the pulses circulate, a tiny portion of each pulse is tapped off by a beam splitter. This tapped light is measured by a detector, and that measurement is fed into an FPGA. That stands for Field Programmable Gate Array. This is a conventional electronic chip that sits right alongside the optical loop.
Okay, so there is still some traditional electronic computing happening here. It's a hybrid system.
Yes, it is. The FPGA acts as the rulebook. It contains the massive matrix of your specific problem, like who hates whom at the wedding. It instantly takes the measurements of all the circulating pulses, calculates their required interactions based on the rules, and generates a feedback signal.
And then what does it do with that signal?
It then uses an optical modulator to inject that feedback directly back into the circulating pulses. It's essentially whispering to pulse number 5, hey, based on the rules, pulse number 12 is currently in a 0 phase, so you really need to shift to a pi phase.
That is wild. The light is constantly being measured, checked against the rules, and nudged by the feedback loop. But how does the system actually arrive at the final collective answer?
It's a process of gradual amplification. You start with the main pump laser, the energy source driving the loop, at a very low power. At this low power, the light pulses are essentially in a quantum superposition state. They're hovering, undecided, between 0 and pi.
Like a guest hovering near the buffet, refusing to commit to a table.
Exactly like that. And then you turn up the dial.
You literally turn up the power.
You gradually crank up the pump laser power. This is the critical transition from below threshold to above threshold. As the overall energy in the system increases, the pulses can no longer remain undecided. They're forced to collapse into a determined state of either 0 or pi.
And this is where the magic of physics takes over from mathematics.
Because of a physical law called the minimum gain principle, the optical system will naturally start oscillating in this specific combination of 0 and pi phases that experiences the least amount of internal loss.
I really want to pause and hammer this point home for you listening, because when I read this in the notes, it fundamentally changed how I view computing. We are not running a step-by-step algorithm to sift through 100 trillion seating charts to find the best one.
No, not at all.
We are literally setting up a labyrinth of light, pumping raw energy into it, and watching the light interfere with itself. The light naturally avoids the paths of high resistance and settles into the path of least resistance. The final ground state of the light is the answer to the mathematical problem. The universe settles into a comfortable chair, and we simply read that as the solution.
It is a profound shift in methodology. And over the last decade, early versions of these coherent Ising machines proved they could solve specific combinatorial problems hundreds of times faster than classical computers. But they had a fatal flaw.
Right, and this is where the protagonists of our story, Hiwei Chuanwang and the team at Beijing Q-Boson Quantum Technology, enter the picture in 2026.
They looked at the existing Ising machines and realized they were hitting a hard performance ceiling. The previous generation of coherent Ising machines utilized picosecond laser pulses.
A picosecond is 1/1,000,000th of a second, right?
Yes, it is incomprehensibly fast. But the Beijing team identified two massive roadblocks with picosecond pulses. First, they required a relatively high average pump power to maintain the nonlinear effects in the crystal. Second, and much more critically, the system had a terrible habit of getting trapped in what physicists call local minima.
Let's define local minima, because the metaphor I usually hear for this is finding a comfy chair, but that feels a little too simplistic. The notes talk about energy landscapes instead.
Yeah, let's use the energy landscape idea.
Let's imagine you are dropping a marble into a large, highly uneven, bumpy bowl. Your goal, the absolute optimal solution to your math problem, is for the marble to settle at the absolute deepest point of the entire bowl. That deepest point is the global minimum.
But the bowl is riddled with shallow craters near the top edge.
Right. You drop the marble and it rolls down, but it gets caught in one of those shallow craters. It's stable. It's stopped moving. It has found a local minimum, but it is nowhere near the true bottom of the bowl. In the context of our wedding, a local minimum is a seating chart where most people are okay, but two people at table 4 are still glaring at each other. It's a suboptimal solution.
The picosecond machines were constantly getting their marbles stuck in shallow craters. When the system transitioned above the power threshold, it would lock into a state that was decently low energy, but not the lowest. The system is inherently lazy in that it settles into the first stable configuration it finds.
To fix this, the Beijing team had an amazing aha moment. They swapped the picosecond laser out for a femtosecond laser. A femtosecond is 1/4,000,000th of a second. The pulses they were firing into the fiber loop were less than 300 femtoseconds wide. That is roughly 1/50th the duration of the pulses used in the older machines.
This massive temporal compression.
Yeah. But I'm looking at the physics here, and I don't intuitively grasp why making the pulse of light shorter stops the marble from getting stuck in the crater.
It really comes down to the relationship between peak power and average power. Imagine you have a garden hose with a steady, continuous flow of water. That represents your picosecond laser. Now imagine taking all the water that flows out of that hose over 10 seconds, stuffing it into a single water balloon, and hurling it against a wall. That is your femtosecond laser.
Okay, I see.
The total amount of water, so the average power over time, is exactly the same. But the impact on the wall, the peak power, is astronomically higher with the balloon.
So by temporarily compressing the light into these incredibly brief, impossibly sharp spikes, they hit the nonlinear crystals inside the machine with much more violence.
Violence is a very good way to describe the effect on the crystal. This extreme peak power yields a massive increase in the efficiency of a process called second harmonic generation, or SHG.
I need you to translate second harmonic generation for us.
Sure. It is a nonlinear process where two photons from the pump laser interact within the crystal and literally combine to form a single new photon that has exactly twice the energy and therefore half the wavelength. This process is absolutely crucial for preparing the DOPO states we talked about earlier. In their 2026 paper, the Beijing team reported that at an average pump power of 120 milliwatts, their femtosecond laser achieved an SHG efficiency of 38.3%.
And what about the older picosecond machines?
At that exact same 120 milliwatts of power, the older lasers only managed 15.3% efficiency.
Wow, so the femtosecond laser is more than twice as efficient at converting the light. But I'm still stuck on the marble and the bowl. How does this increased efficiency stop the system from settling into a suboptimal seating chart?
This is where we have to dive into quantum mechanics, specifically something called the Wigner function. The Wigner function is a mathematical tool used to visualize the quantum state of a system in phase space.
Phase space is another dense term. Let's break that down.
Think of phase space as a topographical map of the possible states of the light. It plots the position of the wave against its momentum. In our coherent Ising machine, the interaction between the pump laser and the signal is governed by a coupling constant, denoted by the letter S. This S value basically defines the steepness of the valleys on our topographical map.
So S is the strength of the interaction.
Exactly. Or to put it another way, because the femtosecond pulses have such high nonlinear conversion efficiency, the amplitude of S increases dramatically. The researchers demonstrated that as S moves from a value of 1 to a value of 2, the topographical map fundamentally changes. The distinction between the +1 spin state and the -1 spin state becomes incredibly sharp.
It's like turning the contrast dial way up on a television. Instead of fuzzy gray areas where a pulse might be lazily drifting between a 0 phase and a pi phase, the options become stark, black and white. Deep, steep valleys.
And this leads to the most brilliant part of their engineering. Because the nonlinear efficiency is so highly tuned, the inherent quantum noise in the system, the microscopic random fluctuations that exist at the quantum level, become much more pronounced during the generation of the DOPOs.
Wait, I always thought noise was the enemy of computing. Like, you spend all your time trying to eliminate noise so the signal is clear.
Usually, yes.
Yeah.
But here, they essentially weaponize the quantum noise. Let's go back to your bumpy bowl. If your marble gets stuck in a shallow crater near the top, how do you get it out?
You physically shake the bowl so it bounces out and rolls further down.
That is exactly what the amplified quantum noise does. It acts as a localized disruptor. It continuously shakes the energetic landscape of the system. If the light starts to settle into a local minimum, a comfy but wrong chair, the pronounced quantum noise provides a violent enough microscopic kick to bounce it out. It forces the system to keep searching, keep tumbling, until it falls into the true global minimum, the absolute lowest energy state where the noise can no longer kick it out.
They built a machine that uses a sharper, shorter laser pulse to amplify quantum noise just to keep the system mathematically honest. That is just staggering. And according to the paper, this efficiency brings another operational benefit regarding the power threshold, right?
Yes, because the nonlinear conversion is so efficient, the entire machine can operate at a significantly lower average pump power. This is critical for maintaining what physicists call the degenerate state.
Meaning the state where the phase is strictly either 0 or pi, with no messy in-between.
Yes, the Beijing researchers observed a dangerous phenomenon. If the average pump power exceeds 226 milliwatts, the frequency spectrum of the optical pulses begins to broaden. It bleeds out. It transitions from a pristine degenerate state into a non-degenerate state.
Which would ruin the calculation. If the spectrum broadens, our perfect plus ones and minus ones get smeared into fractions, and the logic breaks down entirely.
The femtosecond architecture allowed them to keep the operational power well below that 226 milliwatt threshold, ensuring that the spins remained perfectly distinct for the entire calculation.
But reading this paper, there was a massive catch. This is where the beautiful theoretical physics crashes headfirst into brutal engineering reality. They made the pulse 50 times shorter. That means their margin for error became 50 times smaller. We are talking about making a machine that is almost impossibly fragile.
This is the crux of translating a physics experiment into an industrial technology. You have these sub-300 femtosecond pulses racing around a physical loop of glass fiber. The speed of light in fiber is roughly 200,000 kilometers per second. It's fast, but it's finite. The entire computation relies on these pulses lining up perfectly when they hit the beam splitters so they can interfere with each other properly.
And what messes up that alignment? If the pulse is less than a trillionth of a second long, wouldn't a slight change in the temperature of the room cause the glass fiber to physically expand by a microscopic amount, thereby changing the distance the light has to travel?
Oh, temperature changes absolutely ruin the alignment. Furthermore, think about acoustic vibrations. A heavy delivery truck driving down the street outside the laboratory creates acoustic vibrations that travel through the building's foundation and literally wiggle the optical table. When your pulse is only a few hundred femtoseconds wide, a physical misalignment of even a single micrometer completely destroys the computation.
So the machine is useless if it can only operate in a perfectly silent, temperature-controlled vacuum underground. It has to exist in the real world. So how did they armor it?
The Beijing team had to design an entirely custom cavity stabilization system. It's a fascinating mix of high-end quantum stabilization techniques and brute force common sense. First, they built a literal incubator. They isolated the entire fiber optic cavity inside a rigorously temperature-controlled box to shield it from ambient room fluctuations.
And for the vibrations, the notes mention they just layered acoustic foam everywhere.
They used passive damping materials, yes. But passive armor is never enough for submicrometer tolerances. You need active defense. So they implemented a highly sophisticated dither and lock scheme.
A dither and lock scheme. I really need you to unpack that.
Remember the FPGA, the electronic brain managing the feedback loop? They programmed it to run a secondary, simultaneous task. They introduced auxiliary bits. These are extra pulses of light circulating in the machine whose only job is to act as scouts. These auxiliary pulses constantly monitor the loop for submicrometer misalignments.
They are the guard dogs of the fiber loop. They don't do math, they just check the track.
Precisely. These auxiliary bits report back to the FPGA, effectively saying, warning, pulse 4 and pulse 5 are drifting out of phase by a fraction of a micrometer due to a vibration. The FPGA instantly calculates the necessary correction and sends a voltage signal to a piezoelectric transducer, or PZT.
I am looking at the diagram of the PZT in the notes. It's a specialized crystal that physically changes its shape, like it expands or contracts, when you apply an electrical voltage to it.
The fiber optic cable is physically spooled around this PZT crystal. When the FPGA detects a microscopic misalignment, it applies a voltage to the PZT. The crystal expands, which physically stretches the glass fiber in real time.
Wait, hold on a second. The computer is physically stretching and shrinking the length of the glass fiber thousands of times a second to compensate for an acoustic vibration happening in the room.
Yes, it pushes and pulls the fiber at a microscopic level, actively counteracting the environmental noise as it happens. The results of this active armor were phenomenal. They recorded a 4-hour test window where the ambient room temperature fluctuated by about 1.188 degrees Celsius.
Which is more than enough to totally ruin a normal optical setup.
Exactly. But inside the protected, actively stretched fiber cavity, the effective temperature only fluctuated by 0.010 degrees Celsius. They achieved a level of stability that made continuous calculation possible.
So they built the armor, They have the femtosecond laser. They are weaponizing quantum noise to escape the local minima craters. And they have an active PZT stretching the glass to keep the track perfect. It's time for the ultimate test. What problem did they actually feed into this machine to prove it works?
They benchmarked the system using a notoriously difficult mathematical structure called the 100-vertex Mobius ladder max cut problem.
Okay, let's break that down for the audience. A max cut problem is a classic combinatorial nightmare. Imagine taking a massive, complicated web of interconnected dots, a graph. Your goal is to draw a single line that cuts through the maximum possible number of connections between those dots. A Mobius ladder graph is a specific geometric structure that looks like a ladder twisted into a loop.
The twisted, symmetrical nature of the Mobius ladder makes it incredibly prone to generating those local minima traps we discussed. It is a severe stress test for any optimization solver.
And how did the femtosecond machine perform?
Unprecedented. The Beijing team's machine hit an average success rate of 55% in finding the absolute optimal, perfect, global minimum solution.
I can hear people listening to this and thinking, 55%, that's basically a coin flip. That's an F on a math test. But in the world of NP complete combinatorial optimization, where the number of possible wrong answers is greater than the number of atoms in the universe, 55% is staggering.
The paper explicitly notes that this is the highest ever reported success rate for any coherent Ising machine, or indeed any noisy intermediate-scale quantum system attempting this class of problem, an ISQ for short.
And beyond the peak success rate, the thing that impressed me most was the endurance run. Theoretical physics is famous for publishing groundbreaking papers based on one golden run that lasted for 3 seconds before the machine melted.
The Beijing team knew they had to prove industrial viability. They set up the 100-vertex Mobius ladder problem and left the machine running continuously for 8 straight hours.
8 hours of continuous femtosecond pulses. 8 hours of the PZT crystal stretching and shrinking the glass to counteract footsteps and temperature shifts.
Over that 8-hour window, the machine executed 18,000 continuous, discrete calculations of the graph. And the performance never degraded. It consistently found solutions within 99% of the optimal cut value, almost 99% of the time. This wasn't a fragile, finicky lab experiment held together by duct tape. They had built a robust, industrial-grade computational engine.
Which brings us perfectly to the next phase of our deep dive, bringing it to the real world. Why should someone listening to this care about Mobius ladders and femtosecond pulses? Because the Beijing team didn't just write a paper, get published, and turn off the lights. They hooked this optical engine up to the cloud.
Yes, they integrated their physical machine with a cloud service layer using what is known as the Kaiwu SDK. This is a crucial step for democratizing access to quantum-inspired technology.
It means a biologist in London who knows absolutely nothing about piezoelectric stretchers or nonlinear optical crystals can write a standard Python script, submit a biological problem to the cloud, have the Kaiwu SDK translate it into a matrix, and have the Beijing machine solve it using light.
And the team demonstrated 2 massive real-world applications in the paper to prove this exact pipeline. The first application was in biology, specifically molecular docking.
Molecular docking is the absolute bedrock of drug discovery. If you're trying to invent a new life-saving pharmaceutical, you need to know exactly how a specific chemical molecule fits into a protein receptor in the human body. Think of it like trying to fit a highly complex 3D key into a highly irregular lock. But the nightmare is that both the key and the lock are constantly wiggling, bending, and changing shape.
Finding the optimal orientation, the specific docking position that requires the lowest binding energy, is, at its core, a combinatorial optimization problem. You are searching for the lowest energy state. Traditionally, pharmaceutical companies use vast clusters of supercomputers to simulate these physical interactions, which can take hours or even days to simulate a single molecule.
So how did the Beijing team solve a 3D biological problem on a 2D ring of light?
They took 3 distinct biological systems, including highly complex proteins designated as 1N2J and 1LRH, and mapped their physical coordinates into a mathematical format called QUBO.
QUBO, Quadratic Unconstrained Binary Optimization. I need you to step me through this translation. How do you flatten a 3D protein with pockets and folds into a binary sequence of +1s and -1s?
You discretize the physical space. You break the protein receptor down into a grid of possible binding sites. A +1 might represent the presence of an atom from the drug molecule at a specific grid coordinate, and a -1 represents an empty space. The complex chemical interactions, the electrostatic forces, the van der Waals forces are translated into the coupling weights, the S values we talked about earlier.
Oh, so the magnetic pull between two parts of the protein becomes the interaction strength between two pulses of light.
Exactly. The physical rules of biology are encoded into the physical rules of the optical loop. Once translated into QUBO format, they fed the data into the machine. The femtosecond CIM solved the optimal docking orientations for these complex biological systems in under 300 microseconds.
300 microseconds, less than a third of a millisecond to figure out how a complex molecule fits into a protein. If you scale that speed up, you are talking about the ability to screen millions of potential drug compounds against a disease target in a single afternoon. That is a fundamental acceleration of biological research.
Their second application shifted entirely from the physical sciences to the social sciences. They tackled finance, specifically credit scoring.
Yeah, this one completely threw me when I was reading the stack of sources. I can understand mapping physical atoms to physical light, but how does a ring of lasers figure out if a human being deserves a mortgage?
It's fundamentally an exercise in feature selection and risk optimization. The researchers utilized the German credit dataset, which is a standard, highly scrutinized benchmark in machine learning. It contains thousands of instances of loan applicants. Each applicant is defined by 20 specific features, things like their credit history, their employment status, the purpose of the loan, their savings account balance, and so on.
And the goal of a bank is to accurately classify an applicant as a good credit risk or a bad credit risk based on those features.
But you don't want to just dump all 20 features into a basic algorithm, because that leads to overfitting. The model becomes too rigid and fails to predict new cases. You want to select the absolute best combination of those 20 features that gives you the highest predictive accuracy.
Right. Which combination of variables gives the truest signal? Again, we are back to an optimization problem. The seeding chart, the molecule, the credit score, they are all the same math.
They map the features of the credit dataset onto the Ising model and let the light find the optimal feature combination. The optical machine analyzed the dataset and achieved a Kolmogorov-Smirnov value, a KS value, of 0.38.
Wait, hold on a second. You just dropped KS value on me. I'm looking at the notes here, and I really need you to translate that into English for me. What does 0.38 actually mean in the banking world?
A KS value is a statistical metric that measures how well a predictive model separates two distinct groups. In this case, how well it separates the good credit risks from the bad credit risks. A value of 0 means the model can't tell them apart at all. A value of 1 means it separates them with absolute clairvoyant perfection.
So is 0.38 good?
In the messy reality of human financial behavior, 0.38 is an excellent score. In fact, it exactly matched the performance of XGBoost on the same dataset.
And XGBoost is currently one of the gold standard classical machine learning algorithms used by major financial institutions today.
The profound significance here isn't that the optical computer beat classical AI in accuracy on this dataset. The significance is that light matched it. They proved that an entirely different, incredibly energy-efficient physical architecture, a ring of lasers, can perform industrial-level financial risk analysis with the same accuracy as a massive classical server farm.
Okay, I have to push back here because this paints a very specific picture of the future. We've spent this entire first half of the deep dive talking about optimization, and the coherent Ising machine is undeniably brilliant at optimization, finding the lowest energy state, finding the best combination, but optimization isn't everything.
That's true. It's a specific class of computing.
I can't run a word processor on an Ising machine. I can't open a web browser. I can't send an email. And I definitely can't play a video game on it. The Ising machine is an analog heuristic solver. What about normal, everyday, general-purpose computing? Will I ever have an optical CPU in my laptop?
This is where the narrative shifts. We have to leave the refined, highly specialized domain of analog solvers and enter what we might call the Wild West of optical computing. Because while the Beijing team was perfecting analog optimization, a team based in Berlin called Acatonics published a paper detailing their attempt to build the Holy Grail, an all-optical, digital, general-purpose processor. They call it the XPU, or Cross-Domain Processing Unit.
The ambition of Acatonics seems fundamentally different. They don't want to map problems to physical energy states in a loop. They want to perform traditional Boolean logic, the basic A and D or OR and NOT gates that make up classical software using light without ever converting the signal back to electricity.
Exactly.
If you remember our traffic jam analogy earlier, even the brilliant Beijing machine still relies on an electronic FPGA to manage the feedback loop. Electrons are still involved in the governance of the system. Acatonics wants to banish electrons entirely from the computation cycle.
To achieve purely optical logic, you have to invent a true optical transistor. In classical electronic computing, a transistor works by using a small electrical current to switch a larger electrical current on or off. That switching action is the foundation of digital ones and zeros. Acatonics designed a proprietary system using microscopic structures called ring resonators.
How does a ring resonator act as a switch?
It utilizes highly localized, nonlinear optical effects. Essentially, they use one specific beam of light, a control beam, to alter the refractive index of the microscopic ring. When the refractive index changes, it dictates whether a second beam of light, the data beam,
The Acatonics paper dropped. They made a rather bold public relations claim. They stated that with enough memory attached, their optical architecture could emulate a full by-86 processor and run Doom.
yes, the running Doom benchmark. For the uninitiated, it is a classic trope and rite of passage in computer science. Can your new experimental hardware run the classic 1993 first-person shooter video game Doom?
Well, the internet tech community, specifically the highly critical folks on forums like Hacker News, immediately brought out the reality check. They looked at the actual physical demonstrator chip that Acatonics built in the lab. It wasn't a by-86 processor. It was a 2-bit wide machine running a single, highly obscure instruction set called sub-BLQ.
Sub-BLQ stands for subtract and branch if less than or equal to 0. It is what is known as a one-instruction set computer architecture.
I need you to explain how a computer works if it only knows how to do one single thing. How do you build complex software out of just subtraction?
It is theoretically Turing complete, meaning that given enough time and memory, it can calculate absolutely anything a normal modern computer can calculate. You can build addition, multiplication, A&D gates, and OR gates entirely out of chains of sub-BLQ commands. But from a programming standpoint, it is incredibly rudimentary and massively inefficient. You're stringing together thousands of subtractions just to do a basic task.
A user on Hacker News pointed out, quite accurately, that calling this 2-bit sub-lead demonstrator a Doom-capable machine was a massive stretch of the imagination. It's like building a single, perfectly machined gear in your garage and issuing a press release claiming you've built a Ferrari. Technically, that gear could reside inside the transmission of a Ferrari, but you are a long, long way from actually driving.
The criticism from the software engineering community is entirely fair from a practical standpoint. Playing a video game on this specific optical demonstrator is likely decades away. However, the hardware engineers recognize the immense physical value of what Acatonics actually proved in the lab. By creating a functioning, purely optical logic gate and a closed memory loop without electronics, they demonstrated that time-of-flight computation is physically viable.
Time-of-flight computation. I love that phrase. It sounds like something out of Star Trek. What does it actually mean at the hardware level?
In a classical electronic processor, it takes physical time for a silicon transistor to switch states. A microscopic physical component called a capacitor has to literally fill up with electrons before the switch flips. There is an inherent, unavoidable delay governed by capacitance. In the Acatonics optical transistor, the switching relies purely on instantaneous optical parametric nonlinearities.
So the light alters the crystal the exact moment it touches it.
There is no filling of a capacitor. The switching is near instantaneous. The only latency, the only delay in the entire processing system is the literal time it takes for the photon to fly from one end of the silicon chip to the other at the speed of light. That is time-of-flight computation.
And because light generates no friction and experiences no capacitance, the computing is theoretically reversible. It generates zero heat. So yes, they build a tiny 2-bit calculator that can only subtract. But they prove that the concept of a frictionless, heatless, general-purpose computer isn't just theory anymore. It exists in a lab in Berlin.
And that transition from theory to physical reality brings us to the final, most complex piece of the puzzle you brought us. We have analog machines like the Beijing CIM utilizing quantum noise to solve optimization. We have digital attempts like Acatonics trying to do general logic with ring resonators.
So Acatonics showed us we can do basic logic without electricity. But both the Beijing analog machine and the Berlin digital machine share one fundamental limitation. They are still classical systems. They don't utilize quantum entanglement. If we are already building intricate logic gates out of pure light, aren't we just one small step away from building a true, universal quantum computer?
You are tapping into the absolute bleeding edge of the field. The exact same photonic technology, lasers, beam splitters, nonlinear crystals, is currently being used to build universal quantum computers. But it's a very specific branch called continuous variable quantum computing, or CVQC.
We're looking at projects in the notes like the SBOC initiative by Fraunhofer in Europe and the Canadian company Xanadu. How does continuous variable quantum differ from the massive quantum computers we usually hear about from companies like Google or IBM?
The high-profile quantum computers you see in the news generally use discrete variable qubits. They use supercooled superconducting loops or magnetically trapped ions to create a physical state that is precisely a 0, a 1, or a superposition of both. If you try to do that optically, discrete optical quantum computing, you have to try to encode information onto single individual photons.
Which sounds like an absolute nightmare, trying to catch, manipulate, and measure a single, isolated particle of light without destroying it.
It is notoriously difficult.
Mm-hmm.
Single photons are incredibly hard to generate deterministically on demand, and they get lost in the fiber optics incredibly easily. Continuous variable quantum computing completely abandons the single photon approach. Instead of trying to isolate a single drop of water, projects like SBOC and Xanadu use squeezed light.
Squeeze light. What exactly are we squeezing?
We are squeezing the uncertainty. In quantum mechanics, the Heisenberg uncertainty principle dictates that you cannot perfectly know both the amplitude and the phase of a light wave. Squeezed light is a state where we intentionally reduce the uncertainty in one variable, say the amplitude, at the direct expense of increase in the uncertainty in the phase. We encode the quantum information into these continuous field quadratures of a macroscopic laser beam, rather than discrete single photons.
So instead of reading the binary state of a single water droplet, you are reading the overall continuous wave pattern of a steady stream of water.
And this leads to massive advantages in scalability because we are very good at generating and manipulating macroscopic laser beams. In 2025, Xanadu published a breakthrough paper that essentially merged this continuous variable approach with the holy grail of quantum mechanics, error correction.
Ah, error correction. Because without it, quantum computers are just incredibly fragile, highly expensive noise generators. If a stray cosmic ray hits your qubit, the calculation is ruined. How did Xanadu correct errors in a continuous stream of light?
They utilize something called GKP qubits, named after the physicists Gottesman, Kitaev, and Preskill, who theorized them. GKP qubits are a specific, highly engineered type of quantum state, encoded into the squeezed light that has an intrinsic built-in layer of error correction. Xanadu demonstrated that they could use relatively simple, standard linear optics like basic beam splitters and optical phase shifters to entangle these GKP qubits into a massive, highly dimensional structure called a cluster state.
A cluster state. The notes describe it almost like a galaxy of light.
It is essentially a massive woven web of entangled light, and this completely changes how you compute. In normal quantum computing, you have qubits sitting there, and you run them through logic gates sequentially. In a cluster state, you build the entire massive entangled web up front. To perform a calculation, you don't manipulate the individual qubits directly. You perform sequential, highly specific measurements on specific parts of the web.
Wait, if you measure a quantum state, you destroy the entanglement, right?
Yes. The act of measuring a section of the cluster state destroys that specific section. But because of the deep entanglement, the act of destruction teleports the remaining quantum information deeper into the web, performing complex logic gates along the way. It is called measurement-based quantum computing.
So you weave a massive, intricate blanket of quantum light, and then you compute by systematically taking a pair of scissors and cutting specific threads. The path of destruction is the calculation.
That is a highly accurate way to visualize it. You carve the calculation out of the entangled block. And Xanadu's 2025 breakthrough showed that using these error-corrected GKP qubits within a cluster state dramatically reduces the massive overhead usually required for fault tolerance. It proved that light-based continuous variable quantum computing isn't just a niche physics experiment. It is a highly viable, scalable path toward a universal, error-corrected quantum machine.
So what does this all mean? Let's recap this mind-bending journey you've walked us through. We started with the physical heat radiating from a laptop, the thermodynamic wall of pushing electrons through silicon, and the energy crisis looming over the AI industry. We've seen how researchers are shattering that wall using the frictionless properties of light.
We tracked the 60-year struggle to control light, from the shadow-casting stencils of the 1980s to the brilliant 2026 paper from the Beijing team. They showed that by switching to sub-300 femtosecond laser pulses, they could literally weaponize quantum noise. They built an armored, actively stabilized machine that solves incredibly complex combinatorial optimization problems, from molecular drug docking to credit risk scoring, faster and more efficiently than classical servers.
We looked at the Acatonics team in Berlin dreaming of a heatless, frictionless digital CPU that never touches electricity, proving that time-of-flight computation is real, even if they are currently just running a 2-bit subtractor. And finally, we explored the quantum frontier, where Xanadu is weaving massive error-corrected cluster states out of squeezed light.
Which leads us with a profound realization about the nature of computation itself. For the last 70 years, classical electronic computers have forced the universe to do math on our terms. We build rigid, microscopic silicon gates, and we violently shove electrons through them, generating massive heat and friction, demanding that the physical universe conform to our rigid Boolean logic.
But optical computing, especially the analog Ising machines the Beijing team built, doesn't force anything. It sets up the parameters, it pumps in the energy, and it simply lets the physical universe do what it naturally wants to do. Seek the lowest energy state, find the path of least resistance. If we are successfully mapping the German credit data set onto a web of light to determine complex human financial behavior, what happens when these optical clusters scale to the size of a modern data center? Are we just building faster calculators, or are we building physical models of the economy itself, running friction-free at the speed of light?
That is the big question.
Next time you feel the heat radiating from your computer, or you look up at a glowing server farm against the night sky, look a little closer at the light around you. It's not just illuminating the room. It might just be holding the answers to the most complex problems we've ever faced, just waiting for us to ask the right questions. Thank you for joining us on this deep dive.
Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.